Again, it's just, that's all we're just dealing with a new kind of function here. And I'm trying to show you it's not the same as a linear function. Okay, if you have a quantity that's changing, like a population, for instance, by a percentage, it's going to be an exponential function. So this is where exponential functions come into play. A quantity that grows or decays by the same percent at regular time intervals, okay? This is said to have exponential growth or exponential decay. This is actually what I got from the other book, that book by, I think Martin, got the middle name, I think it's Martin Gay, the person's name is. I think it's called Beginning and Intermediate Algebra. So it's another book I have. This is where I got that definition from. So anyway, again, if you have something like population size, it's growing or decaying by the same percent each year, at regular time intervals. So like each year, each day, each month, something like that. Then we have exponential growth or exponential decay, right? And that's what we have in this problem. In part 2, we're assuming the population is changing, or in this case, it's increasing, which really is the same as growing, by 5% each year, the same percent at each year, at regular time intervals. So in that case, our function, for the example, would be exponential growth, and our function, here I would call it f of x, is going to look like this. In part 1, I called it g of x. In part 2, I'm actually going to call it f of x. So it has to look like this. The a is our initial value now. Okay. A is what happens at time 0, the beginning. 1 plus r, that's the base also. It's what we call the growth factor. R is actually that growth rate, which is often written. It's often written in the problem as a percent, but in the formula, you write it as a decimal. You write it as a decimal. Okay. Right, so in the problem here they tell you the population's growing or increasing by 5%. So in our formula, as you'll see, R is going to be 0.05. That's what R is going to be, 0.05. Now, you could also have exponential decay. I mean, not with population growth, but we'll see some examples next time. We'll see them later. But you could have something called exponential decay. I mean, one application of that, as we'll see, is radioactive decay, or like half-life. In this case, the only difference is instead of 1 plus r, you have 1 minus r. And 1 plus r, that's actually called the decay factor, growth factor, decay factor. Here, r is that decay rate. It might be written as a percent in the word problem, but in the formula, you have to write it as a decimal, meaning you convert it to a decimal. So again, going back to this for part 2, right? We're told the population's increasing by not a fixed amount per year, but 5% per year. So a linear function won't work. We're using exponential growth, right? This is what our function looks like. This is the formula. We just had this. So A is the initial value, which in this case is 500 in the context of the problem. R is 0.05, right? It's increasing by 5% per year. So in this case, R would be 0.05, as you can see. And this is what we get. So that's what exponential functions are. Okay. Now, some of the examples from yesterday I want to go through. Are there any questions so far? Okay. Now, In other sources and other, I guess, math classes, for instance, this is actually a more general way of defining an exponential function. So many people out there will define an exponential function this way. They'll do a times b to the x, where a is f of 0. Again, that's the initial value. You know, that's the value when x is 0. And this is also just reminding you that if you take any non-zero number, like b to the 0, you'll get 1. So you'll get a back when x is 0. And here, b, some people call it the base. It's positive, but it can't be 1. I mean, because if b were 1, then this would be a constant function. That is, b to the x would just be 1 always. But b has to be positive. And if b is greater than 1, then we have exponential growth. So again, the exponential function in this form is a little more general. A lot of people define it this way. But if b is greater than 1, you have exponential growth. Namely, you can write b this way, just like from before. And r, again, is that growth rate written as a decimal. I mean, you could actually, we'll do some examples shortly, but you can actually calculate what r is. You can do that. I mean, it's just basic arithmetic. I did write the formula here, though. And if instead b was positive, but it's less than 1, then you have to have exponential decay. It's decreasing, in other words. But again, you can calculate b. Instead of 1 plus r, it's 1 minus r. No, see, no, that's what b is. Yeah, that's right. That's right. Where r, again, is that decay rate, you know, that percent, but it's written as a decimal. And again, you can calculate r. It's 1 minus b. I should note that r, I should tell you this, r is always going to be positive. So if you do one of these and you get a negative, then something is wrong. And now, again, why am I saying this? Because if we have this exponential function, you can still figure out what r is. And I'm basically showing you through these formulas. It's really not hard to do. And that's what I was trying to explain last time, although I don't think last time I was too successful, but hopefully I'm more successful now. But let's do some examples where you have this kind of exponential function. Excuse me, it's written this way, but we want to find r. So let's say this was the function we were given. Okay, so again, b, the base, right? That's going to be an a times b to the x. That's less than 1, right? Well, if it's less than 1, let me go back to this slide, where in this case, it's positive and less than 1. So b is 1 minus r. But what is r, in other words? R is going to be 1 minus b. So basically, to get r, you would have this, which is 0.15. So again, I'm just using this formula. So in other words, the function values in this case, r is 0.15. This means the function values are decreasing by 15%. So the decay rate is 15%. Right? So we have this exponential function. I mean, the initial value is 100, but we're trying to get r here, and you have to look at b, which is less than 1. It's 0.85, so it's less than 1. Since it's less than 1, we can calculate r. We just do this. Now, if it's greater than 1 instead, right? If it's greater than 1 instead, like over here, 1.3. So that's our b in this case. How we get r, that's 1.3b minus 1. I'm just using this formula. Like so. Which is 0.3. So in this case, the growth rate, it's growing because your B here is greater than 1. We get 30% for the R. Because again, it was 0.3. So as a percent, it's 30%. And in this case, the function values are increasing by 30%. Right? And that's also what I was trying to show you with this chart. Remember, I gave you, well, not chart, I guess, table. Right? We had these examples, but for each case, you can get the initial value. You can get the growth or decay, whether it grows or decay, and you can calculate R, right? Here, 1.25, right? Well, excuse me, the initial value is 615. That's the value in front. Now, since the base, the growth, since the base here, 1.25, is greater than 1, we have growth. And so because of that, we can get our R. Namely, to get R, we would take B and subtract 1, right? Again, I'm just using this, this formula right here. I mean, it's either going to be B, your base here, minus 1, or 1 minus it. And you take the one that's positive. I mean, I hope that made sense what I just said. I think it did. So we get 0.25.